Thanks for joining all and putting aside the time. So this week, Git plumbing, I guess I'm sure just about everyone on this call, I'm just trying to think if there would be any other version control system in use on any other JUXT project. I very much doubt it. So I'm sure everyone on here has quite a lot of experience with Git. This might be a concept that you're familiar with, but Git, as Matt will explain, is divided actually into these porcelain commands. You can think of this as like the plumbing system. There's the porcelain that we interact with, like the kind of things like the toilet and the actual the basin, the things that we interact with a plumbing system. So that's known as the porcelain, and then there's this plumbing underneath. And most of us never really have a reason to interact with the plumbing, but having a sort of good knowledge of what's going on underneath the porcelain that you're interacting with is actually very, very useful, and certainly helps you out, as I've mentioned in Slack, certainly helps you out if you get into some sticky situations with Git. So and not only that, but I think Git is also an incredibly successful and fascinatingly well-designed piece of software that draws upon a lot of the concepts that we're familiar with from functional programming, immutability, and it's just a really well-designed piece of software. So really, it's a really nice system to look at in a bit more depth. So yeah, thanks very much, Matt, for putting together a session on this, and over to you.
Thanks, Joe. That was a perfect introduction. So yeah, Git was born back in the day when by Linus, who wrote the kernel. And I think his joke is that he's now got two pieces of software named after himself. It's actually quite interesting. The kernel was struggling, I think, with the existing version control systems. And a new sort of commercial one came out that did things in a different way, and some of the main kernel developers adopted it. And then, of course, that, as the world is, causes a big furore because there was non-open software being used to maintain arguably the most important piece of open source. So I think Linus, after getting very sick of all the anger and vitriol, just sort of smashed this out in like a week. And it was quite a deviation from the existing version control systems at the time. We'll get onto that in a bit. I think the natural thing to do when you're looking at version control and you're working with the differences in files is to focus on those differences. And perhaps like some old PCSs even had like a full-on algebra or domain-specific languages to describe the differences between files, and those things quickly descend into great complexity. The other sort of big thing that those version control systems did is they very much had a star topology where you have a central location, and everyone kind of has to sync their changes to that central location. And most people today work with like GitHub, and that kind of is the star in this topology. But lots of people, you don't have to work like that. Git is fully distributed, and the way it works enables that. So like Joe said, there's some sort of porcelain commands and there's some plumbing commands. I'm not going to look at too many plumbing commands, only like 2 or 3. You don't need a lot. This is just really to show you how kind of what's going on, under the hood, and let you kind of just picture in your own head a little bit better what you're doing when you commit some files. Nearly all of this talk is taken from the Git book that's available online for free, and you just have to kind of find the time to read it, which is hopefully I can distill down what I think important enough that you don't have to. So we'll crack on. So the heart of Git Git is a content addressable file system. Now that sounds, what is that? Like a typical file system kind of looks like this, right? You basically have a name of a file, and then there's this like understanding that the data for that file is stored on a disk somewhere. You're kind of looking up a key to a value. So a content addressable file system is a little odd to think of. It's basically you have your content, and then you use that to look up what's kind of stored on the disk, right? That's kind of a strange thing. So why do we want to look up the contents of a file using a file's own contents? Well, this is exactly the sort of thing a version control system kind of wants to know. Like if you have a file or some data in a file, you want to know if it's already in the persistence layer of your version control system. And what better way to do that is than to use the kind of content itself. That's just set membership. So you want to do this, but you obviously, if your files are huge, very big, you kind of still want efficiency and speed. So you can just use digests. Digests are the result of hashing algorithms. So you can get some arbitrary data of any size, and you can return a fixed size string that kind of represents that. This is a function. Any data that you give it will always give you the same result every time you call it. There is a thing where like two different sets of data might produce the same digest. We're not going to worry about that. There are rumors that some massive Git file systems have actually clashed, but I don't know if whether you believe that. So, no, bear with me. I'll take Harry to A&E. So if you take so here's our hello world example. Here's our content, hello world, on our back end in a VCS, it's stored as hello world. So now we'll take a hash of hello world. We'll get our digest. In this case, it's just xjkt. And our digest we can use our digest now to kind of look up the data. So we're still using our data to just very quickly check if our backend, our persistence layer in our version control system has the data. So why is this useful? Because if you want to know if the file you're working on has changed in any way, all you need to do is calculate the digest and then look it up in the back end. If the file already exists, it's unchanged and there's no differences. And if the file does exist in some way, I'm sorry, if it doesn't exist, then that file has changed. We've got a different digest. And we can just put back the new content. So rather than working with diffs of files, I think Linus and Git took the decision to work with whole files. This is really nice because you don't have to use complicated diffing algorithms to work out if there's been a change. Like when you do come to doing other things that you might want to do in a version control system, like working out the actual diffs, like those calculations can be deferred until the point in time where you actually need them. So we've kind of like made this nice decoupling. What else? What other things do we have that's like advantageous? Well, if we're just looking at the content of a file and we're forgetting about all the other things that a file comes with, like the ownership, the name of it, the permissions on it, those sorts of things, then you know it doesn't matter if you rename that file in your working space, right? The digest is still going to be the same. And that way you can kind of almost for free track content across file renames, which is really nice. Another thing is you kind of get deduplication for free. Like look at sort of like GitHub with masses and masses of repos. Well, there's like the hello world file, right? That's going to create a digest. That's going to be stored once for every single person in the world on GitHub, right? So that's kind of nice. So we can have a look at the creation of a hash in Git. So we can say sort of, let's take our hello world, and we'll pipe it into this Git command called hash object, and we'll put the output on standard in. What we've done here, it's just super slow. Okay, so there we go. This is our hash, our digest, the result of our hash that represents hello world. And if we kind of change this to something else, we get a different number. Okay. So a sort of a command we can do here is we can actually put a W on the end. And this will take our hash object that we've just created, and it will actually write it to Git's persistence layer. So where does this, what's actually happened? Like we've now stored our hello world. So let's go and find it. Let's see where it looks. So we can go into .git and we can list it out. And in here we have an objects file. Okay. And here, this is kind of our file system. This is our back end. We've got our keys to look up. So if we take our hash, look, the first two numbers are 25. So bear with me while I got my Zoom's in the way. Okay, so we can go into 25. Oh, where did it go? Hold on, let's have a quick look. I wasn't in the directory. 25. And then we're looking for the rest of that hash, C2, C9. Let's have a look what we've got in here. So there we go. So this, if we look at it, is actually a compressed file. And the size is going to be tiny. Yeah, 30 bytes. So this hash object has created a digest, used the digest as like a lookup key, and it's put the data in Git objects. And it's used this kind of schema of the first two digits of the digest and the remaining 38 digits for the actual content. So everything you ever put into Git is going to live in this objects directory. And quite often those objects, like if you very badly mess up your Git, those objects are still going to exist in some form or another until they get cleared up by some Git garbage collection. Well, we don't have to worry about that. So nearly always you can kind of recover from a bad situation. So because this is compressed, we can't actually look at the content, but we can use a git command to kind of view it for us. So if we do cat file -p, and then the digest, I'm not going to fill it all in. Oh, I might have to. Sorry, it starts with 25. C2, C9. There we go. So that's our object. That's our file. That's our content. It's in the persistent store of Git. It's in the /objects directory. And if we kind of look at our system here, where am I? we don't see that in our sort of git status command, right? We've sort of bypassed all the other sort of content tracking stuff, and we've literally just put in some data into our state layer. So well, we've got a way of taking some content, making a hash object. How now we can read and write. What do we do about file names and the kind of file system hierarchy that we're used to using? And just metadata about the content in general. So what we have, or what Git has, is a data structure called a tree. And this is a simple model of a tree. So this blob here, this is our kind of hello world. We have a file name called readme that points to it. Similarly, we have another file, another load of content in this blob, and we have a rake file pointing to that. And then here in our tree, we have a name that this time points to another tree. And then that has a name called simple git, which points to a blob. So if a tree points to a tree in the Git data structure well, then this is our kind of subdirectory. And that's it. It's as simple as that. So we can kind of see what that looks like. Let's see if I can copy this, paste it. I can. So here we have the tree object of my main branch and this Git repo I'm using. So if we can actually look at the directory as well, that's fun. So this is our hash that we talked about that represents the content. So this is the lookup key for the content. This is our name, and it points to a tree, another tree. So this is a directory. So 3 trees is going to be a directory in our working. And here you can see it's a directory. In fact, nearly everything here is a directory. If we run this command again without chopping off the data, at the bottom here, we can see that we have this our tree object the points to all these directories and to these 2 files. And over on this left-hand column here, right, we've got the permissions of the files. Those of you familiar with Unix will kind of recognize this sort of octal notation. I think this is like read, write, read 644. We probably did an ls myself. You can kind of see that. So this tree object, if we build this up, right, this gives us a snapshot in time of our workspace. So that's exactly what the index or the staging area is when you're working in Git. You are basically altering files, happily developing away. And as you run your git add command and put the files in, you're creating exactly this, sort of like a partial tree. Like it's the blueprint from what a tree will be. Sorry, 2 seconds. What are you doing? My bad. So yeah, so when we run git add, what we're actually doing is we're putting the content object on the back end, and we're adding this metadata stuff to the index, which when we finally get round to writing the index, we'll use this to actually create the proper tree object. So let's have a look at that. So here we're going to write some content to the back end. The content is JUXT forever. And here we've got our digest, and we'll be able to see that in .git/objects. And now we're going to write the index. So we're going to update the index with the meta information about this digest that we've just put into the sort of persistence layer. So we're going to name it JUXT.text. We're going to add some permissions data, and then we're going to do it. So let's do that. So let's have a look at the status now. Right. So here we are. We have a new file in our index called JUXT.text. Now, because we haven't done this through the workspace, and we've been using the sort of plumbing commands, we don't actually have it. Like, it doesn't exist in our file system right now. So if we want to take that index, kind of our tree that we've sort of partially built, and write it out, we can, and we use the command write tree. Okay. So if we look at this tree file that was created by the index, which we updated with our metadata about the content we stuck directly into the persistence layer, we can see what that looks like. Okay. So this tree object, this thing that sort of Git takes care of for us, now has a reference to JUXT.text. So pretty cool. So this tree represents a snapshot of our workspace, or normally does. It doesn't in this case because we haven't had JUXT.text in our workspace. So
Matt, if I'm understanding correctly, then the index is a different thing. It's different from the tree. So you had to do like two separate steps. What is the result of updating index then in the .git directory?
sorry. So the index is like a file that you build up that will represent the tree object when you decide to create it. So it's the sort of commands that you would use to build the tree object. So when you're typically working in Git and you do add and whatnot, it puts things in this index file. And then when you're happy and you commit things, it will write the index file into an actual tree object that will be stored in the persistence layer, and that will represent a snapshot of the file system. Is that what you asked?
I'm not sure. I was wondering why there are two different steps. So update index and write tree. What the difference is between the two? So with update index, we saw the JUXT.text file appear
Right.
in the
Okay.
staging
So
area, right?
because the tree represents a snapshot at a point in time that you want to save, for a long time, right? You want to use, you just naturally don't work like that, right? You naturally add in files and into your normal workspace, right? You might start creating like deployment.yaml and all these things, right? And as you build it up, you then get to a state where you want to like craft a commit, or you're happy with you would like a snapshot at this point in time. So when you add into the index, it lets you build up this kind of view of the tree object that you want to save. I hope that explains it. It's just to give you, I mean, you could, every time you save a file, you could write the tree object, right? But that's just not very useful to humans, because there would just be so many snapshots of your workspace over time. So it's better to like allow that to be delayed and for you to be able to sort of craft when you write a tree object. Maybe that'll become a bit clearer as we kind of look through some of the diagrams.
Okay.
So there's still something missing, right? There's still an object missing here. So what have we done so far? We've got our content, we've added it to the persistence layer. We have decided that we want to keep that content, and we've kind of given it a file name, given it some permissions, and added it to the index. And then we've kind of like repeated that process a whole bunch of times as we build up our program or our software. And then we sort of say, okay, we're at a good point. Let's take this index, this sort of blueprint for a tree object, and let's write that tree object again to the persistence layer. Okay, so over time, if we just kept doing that, we would have a lot of trees. You know, what's kind of missing from these snapshots of your file system that you've put into trees are an ordering. Like, these trees are kind of not related in any way. There's nothing in here that lets you see which tree came before, right? There's just no timeline here. You would just have a huge amount of unrelated trees, each of which is a snapshot of your workspace. So we have a commit object to the rescue. If we order these trees that we've been writing, then we have a full history of state. So a commit is a mechanism that Git uses to provide that. So here's a picture of how things look. We'll start here. So we've got version 1 of a test file. Okay, we write it to our backend. We add test.txt into our index. And we're like, right, that's enough work for today. So let's take that index and convert it into and write the tree object out. So now we have this tree object, D8329F. And what we'll do also is we'll create a commit object. And all a commit object do is kind of point to a tree object, and contain some of the useful information that you kind of want on a BCS. It contains like who added it, like when you added it, a description why. And we'll see what a commit object looks like in a bit. So you come back the next day, you start some work, you create a new file, FA49B0. You write your index, new.txt. You modify test.txt with some new data, version 2. It gets a new digest. And then you write that tree out. You know, once your this index is kind of like you're happy with, and then you write the tree out to the persistence layer, and then you create a new second commit object. And that says like who did it, and this one Git keeps track of for you, says okay, the commit object that came before me was this one. So if you can keep track of which commit you're on, you can kind of look at your workspace, look at the tree. You could check out all these files and have this workspace mirror the contents of the tree, or you could follow the commit child link down to this commit, and you could get this tree, and then you could ask it to make your workspace look exactly like this tree structure here, right? And this is essentially what you're doing when you're checking out and branching around and whatnot. So the third commit here, what do? We keep version 2 the same. So this is brilliant. This snapshot can reuse the data. We keep the new file the same. But what we've done is we've resurrected, we've actually created a subdirectory called back, and we've resurrected this first file, and we've got a pointer to it. So our third commit now has a new directory and called back with the original test.txt version. Yeah, so like we're just these kind of really simple data structures. We've got like a blob of data, like zipped up. We've got a tree, which is essentially a file name, and some permissions and a pointer to the blobs. And then we've got a commit that links that provides an ordering over the trees. Right, so let's have a quick look. So if we do git log, and then we do git cat file -p 721. So we're going to look at this commit object 7C721. Okay. So you can see this first line here. This is the tree it points to. This is the person who authored it, and this is the person who committed it, and then this is a description about what went on in the work. So yeah, right. So we still have a little bit of a problem with our kind of structure in that we have these commit objects that provide an ordering, but we kind of need to know where in that list of commit objects we are. So this is what the refs sort of help us with. If we have a look at what we've got in this particular, so we have floppy and main and tags. And if we look at what our branches are, we have floppy and main. So refs are really very simple. The sort of the heads ref point to a commit. So this is actually let's have a quick look where we are. Branch main, change to be committed. Okay, so if we look at this file, file P, this. Okay. So this is the head. You'll sometimes hear people talk about the head. This basically means your ref in this kind of nice, easy to sort of understand terminology is a symbolic link pointing to a commit object. And all that branches are, when we look over here, are pointers to different commit objects. So if we go to Git, if we look at refs, it's floppy, we see that we've got 727C. If we look at, when we looked at the main one, we had this one. Sorry, this one. So it's easy, almost like this is why some people say like branching is for free in Git, right? Because I can literally just go into here and copy floppy to floopy 2, and then there you go, I've got a new branch. Nothing is changing on behind the scenes, right? All that I'm doing is I'm choosing what commit object it will look at. And by manipulating the which commits you look at, which commit objects, you get an entirely different kind of snapshot history. So this is kind of like the final picture. We have our commits, and then because these are objects with like digest names and stored on the persistent layer, they're not very easy to talk about. So what we do is in the .git refs directory, we maintain a list of human readable names that just point to the commit object. And the different things in that ref directory represent different things. So we have tags in there too. So here you can see some tags. There's no tags in this particular directory, but if we were to create a tag, which is like a point in time, all that would be the tag name, like version 1.12 or v1.2, and it'll have a pointer to a commit object. So there's one kind of like final piece of the puzzle is like, how do we know what we're working on right now, today, like this instant? And there's one more kind of indirection, kind of reference, and that is git head. And that is the thing that says, okay, this is what you're working on now. And this is just a symbolic reference to refs heads main, which we know is a reference to a commit, which we know it points to a tree, and a tree actually represents a snapshot of all your data. So when you sort of jumping around, if I, where am I? Can I sort of get branch, new branch, and then look at git head? I've not checked out. And then look at git head. So there you go. Look, I'm now on git head. If I probably, let's see what happens. If I jump into here and change that back to floppy. Oops. And then do git status. I've changed my branch. It's as easy as that. Okay. Sometimes when you get a detached head, this is an interesting thing. You will let's have a look, git log. We don't have enough commits. what happens if you check out a particular particular commit? Git log. Desperately want some more. Let me just get status. Git log. If I check out 7C721, and then I look at the head file. Now this is not a symbolic reference. This is a pointer to a commit now. So all that means is that I'm not looking at the latest commit object for this particular branch. Right. So we'll skip the tag objects due to time. So what we've got, this central concept of a sort of content addressable file system. The objects are zipped up blobs of data, and they're addressable by their digest. The objects are grouped via this tree object. Whilst you're working, you build up this index structure or the staging area, and then you use that as a blueprint to create your tree object, which is a snapshot in time of your workspace. And then you use a commit object to provide a relationship between all your tree objects over time. Because commit objects are sort of named by their digest, there's yet another layer of indirection called refs, and they're just friendly links to the latest commit object or a tag. And then finally, there's this head file in your local file system that points to the ref that you're using, or sometimes a commit if you've checked out back in time. So I was going to do a lot of look at this stuff over rebasing and resetting and how these concepts work, but I am well out of time. 45 minutes.
Could do a second part.
Yeah, if people are interested, I could perhaps do another one, just sort of looking at these. So hopefully that's provided you all with a bit of an understanding of what is going on behind the hood. It's pretty simple. There's like a lot's taken at once, perhaps, but there's only 4 kind of data structures, each doing their own thing. And yeah, that's it.
Brilliant. Thanks very much, Matt. Unfortunately, I need to run to another call right now, but as Felix said in the chat, very, very well explained. An excellent, I think, like staged sort of introduction to things, and very, very useful. I think you're right. You've got some great further content there on branches and things, so we should arrange a part 2, advanced Git part 2. I need to drop off. If anyone's got any questions, then yeah, feel free to ping us some things in Slack as well. And yeah, thanks again, Matt. Really, really useful, I think, for everyone at Git, 'cause I'm sure there'll be a lot of people that'll be referring back to the video of this one as well. So yeah, cool. Cheers all. We'll see you in a couple of weeks.
See you. Bye bye.